Have you ever wondered how efficient an AI could get without draining your wallet or your computer's power? Well, Microsoft just revealed a new AI model called BitNet, and it's changing the game for artificial intelligence. The best part? It doesn't need super expensive hardware or massive amounts of energy to work. Let's break down how Microsoft's team managed to create the most efficient AI ever. Microsoft's general AI team recently introduced BitNet, or B1.58 to B4T, which sounds more like a Wi-Fi password than the name of an AI model. But trust me, it's more than just a weird name. This new AI is not only groundbreaking, but also surprisingly simple in its design. In a world where AI models demand huge amounts of power and memory, BitNet challenges the status quo. Imagine running a powerful language model using just a regular CPU without draining your electricity. And here's the kicker. It achieves all of this with just 3 simple values for its weights: -1, 0, and +1. To truly understand the impact of BitNet, you need to know what makes it different from traditional AI models. Most large language models use a weight system that requires 32-bit, 16-bit, or even 8-bit precision. But what if you could cut all that down and still get powerful results? That's exactly what Microsoft did. Instead of using the usual precision, BitNet uses only 3 possible values for its weights: -1, 0, and +1. This means each weight can be represented with just 1.58 bits of information. Now you might be wondering, aren't we already using 1-bit or 4-bit models? Well, yes, but typically these models start with full precision weights and then get compressed afterward. This method can save some memory, but it usually comes at the cost of accuracy. Microsoft's team, however, took a different approach. They trained BitNet from the ground up using these trinary weights. This means no legacy floating point numbers to mess with, and the result is a super efficient model that still performs well. When it comes to hardware, efficiency is key. Typically, large models with billions of parameters need a lot of memory and power. A standard model with 2 billion parameters might require 2 to 5 GB of RAM, but BitNet, it only needs 0.4 GB of memory to run. This drastic reduction in memory usage means that the model can comfortably run on regular CPUs, even on devices like an Apple M2 chip. In fact, during testing, BitNet was able to generate text at a speed similar to a human reading a line in a paperback book at 5 to 7 tokens per second. And the energy consumption? A massive 85 to 96% lower than other models that rely on more traditional floating point precision. To put it in perspective, it's like the difference between the energy usage of a Prius idling and a muscle car accelerating. But speed and energy efficiency mean little if the answers from the AI aren't up to par, right? So how did BitNet perform on standard benchmarks? The results are impressive. In various tests like MMLU, GSM-8K, ARC Challenge, and PyQA, BitNet landed an average macro score of 54.19%. While that's just a fraction behind the best float-based models, BitNet excels in some areas where others struggle. For example, in logical reasoning, it outperformed the competition in tasks like the ARC Challenge, where it scored 49.91%, and Winnow Grande, where it scored 71.9%. Even in math, BitNet was a top contender, scoring 58.38% on GSM-8K, beating many other models of similar size. When compared to other models that use 4-bit post-training techniques, BitNet really shines. For instance, the Quen model, which was reduced to 0.7 GB using standard 4-bit quantization techniques, ended up losing significant accuracy, dropping 3 points in performance. Meanwhile, BitNet maintained its accuracy while using much less memory. This proves that training with trinary weights from the start is a more effective approach than compressing a full precision model afterward. Now let's break down how BitNet actually works. Think of a traditional AI model as a huge warehouse filled with shelves. Each shelf has big jars of precise numbers that the model uses to make decisions. Every time the model needs to answer a question, it has to grab all those jars and process them. It's like hauling a ton of stuff around every time it needs to think. Now, imagine BitNet. Instead of jars full of exact numbers, it uses tiny color-coded poker chips, red for -1, white for 0, and blue for +1. These chips weigh almost nothing, so the entire warehouse shrinks down to a tiny size. The result is a much lighter and more efficient model. A little worker called the ABS mean quantizer picks the right chip for each spot, and it does this live, while the model is running. To make everything run faster, the model squeezes the messages traveling between shelves into small, efficient 8-bit numbers. This helps keep everything moving quickly without any bottlenecks. Training BitNet is a bit like teaching a child how to read. First, you speed through every book in the library to get the basics. This is like the model's pre-training with 4 trillion tokens. Next, you slow down so the child can absorb more detailed information. This phase is like the model's cool-down period. Then, you give them practice exams with clear answers so they can start talking to people without rambling. This is the fine-tuning stage. Finally, you guide them by showing pairs of answers and saying, "People like this one better. Do more of that." This last step is known as direct preference optimization, where the model learns to refine its responses. One key to BitNet's success is that it never switches back to using full precision weights. It stays with the chips and Lego bricks throughout the entire process, which means nothing gets lost in translation. Running BitNet isn't as simple as just plugging it into a regular computer. Since most AI models are designed to work with larger precision weights, Microsoft had to write custom software to make BitNet run smoothly. The software bundles 4 of the tiny poker chips into 1 byte, then sends that bundle across the GPU highway. Once it reaches the math engine, it unpacks and multiplies the chips with those 8-bit Lego bricks, allowing BitNet to generate results on even a regular laptop or Mac with only 400 MB of memory. While BitNet is already showing incredible promise, Microsoft isn't done yet. The team plans to test how well the model scales when it reaches 7 and 13 billion parameters. They're also asking hardware manufacturers to create specialized chips for low-bit logic so the math doesn't have to pretend that trinary values are just 8-bit numbers. There's still more work to be done, like expanding the model's ability to handle longer documents and exploring multilingual tasks. However, for now, BitNet offers a glimpse of what the future could look like for AI on everyday devices. So, what does BitNet B1.58.2b4t tell us about the future of AI? It shows that we don't necessarily need expensive data centers or super-powered GPUs to run sophisticated AI models. With just a simple CPU, a small amount of memory, and a fraction of the energy, you can run a model that performs nearly as well as the best full-precision models in its class. This is a game changer for everyday devices like smart keyboards, offline chatbots, and edge devices. Once hardware catches up, we might even see a new wave of AI models that don't require massive resources to be effective. If you're excited about the potential of BitNet and what it means for the future of AI, don't forget to hit that like button. Also, feel free to drop any questions or thoughts in the comments. I'd love to hear what you think. Thanks for watching, and I'll catch you in the next one.